Hello everyone, we are Team 6 and we are going to present our project Viral, which is a variational inference for reinforcement learning. Before jumping into the project, I would just like you to give you background about reinforcement learning. Reinforcement learning is a sequential decision making problem where the agent learns what actions to take in a given environment to maximize the reward, as you can see in the corresponding figure. For the project topic, we decided to replicate Viral, which is a variational inference framework for reinforcement learning, which provides numerous benefits over existing methods. We then investigate and extend Viral to multi-agent reinforcement learning setting. And we further improve the results of the original paper by doing an ablation study on the residual error norms. So, to give you a background about the variational inference frameworks, the first family that exists is the maximum entropy RL, which is called as the Merle framework. So, Merle promotes stochastic policies. Basically, it learns the optimal policy as the highest expectation of the long term reward and the long term entropy, as you can see in the corresponding equation. It has various benefits, like it provides you better exploration, it provides alternative ways for accomplishing the task, and it also leads to better generalization in case of, for example, when there is a presence of obstacles and you need a stochastic policy, which can actually do way better. And the proposed method Viral actually optimizes the following objective. In a nutshell, basically, in the E step, we keep the parameters of our critic constant while updating the actor parameters by maximizing the elbow with respect to theta. In the M step, we maximize the elbow with respect to omega while holding the parameters of theta k plus 1 constant. Hence, basically, the outer expectation is taken with respect to the posterior found in the E step. It has various advantages over the Merle framework that I introduced before. Basically, Merle goes through time, and Viral is only dependent on the current Q function. It doesn't consider the discounted future entropy into account. At the beginning of training, the residual error is large, and therefore the entropy of the policy is high, promoting exploration. In other simple words, as error gets lower, entropy gets lower, and policy becomes more and more deterministic. Proposed method has various advantages, like it naturally learns the optimal policy. Temperature is not at all a hyperparameter. Function approximator is explicitly used. And stochastic policies are used for training. Discounting is easily incorporated. And finally, it optimizes the reverse form of KL, which makes more sense in terms of the reinforcement learning setting. For the replication plan, we actually use the code available by the authors. We use the Mujoko simulator for which we secured the license. The experiments were built on the existing RLKit framework. We found that the RLKit on GitHub has actually significantly diverged from when this paper was published. So we actually had to find the commit for which the code actually worked. For replication of the experiments, we use the Mujoko V2 environment on these tasks, which is basically ant, humanoid, and humanoid stand-up. And we expected to run into problems as the current version of the experiments crashed and gave various bugs. But now I'll show you about our replication. So for ant version 2, we reproduce the average return similar to the original paper for both Viral and DDPG. But we found that the SAC actually underperformed the results given in the paper. And DDPG also did not do as well as what we expected from the results in the paper. For humanoid, it was sort of a surprising task for us. The paper actually claimed that DDPG was the only algorithm that failed to learn this task, but we found that DDPG was actually the only algorithm that worked on this task, and SAC and Viral actually failed to learn the task at all. And finally, on the humanoid stand-up, we observed that Viral actually outperformed the results that were reported in the paper, but we also found that SAC outperformed the paper results by a large margin. We believe that these discrepancies in the results is maybe because of the lack of tuning that the original authors did. We tried our best and tried a range of hyperparameters for all these environments and for all these baselines, and as a result, we got these results.
So we encountered numerous difficulties throughout our project. For one, the author's code did not run as published. So the code they provided calls methods that don't exist in the class hierarchy. The Docker file that they provided does not have the dependency versions listed, and the repo depends on numerous things which are sensitive to version, including Gim, MuJoCo, RLKit, etc. And the paper doesn't list all necessary hyperparameters. So they have a hyperparameter section in the end, but this residual error norm, which is called beta, was not listed at all. So we had to investigate that for ourselves. And many of the baseline algorithms perform differently than stated in the paper, meaning that at best, some of the baselines in the paper are underreported. So we tried to contact the authors to discuss the versions with them, and we wanted to ask them some more questions. And the second author told us to ask the other author, and the other author gave us one uninformative response and then went silent. We followed up with them by email, and they were likewise unresponsive, which is unfortunate because we were really interested in their work. The computational cost was another challenge for reproducibility because each experiment took about 10 to 30 GPU hours. So we managed to run 3 environments on 3 models with an average runtime of 11 GPU days, only for the reproduction part. So for the improvement, we wanted to extend VIRL to multi-agent VIRL, where the problem setting is that multiple agents have an easily learnable dense reward for specific tasks, but difficult sparse rewards for the overall task. So our solution is to utilize VIRL to create multi-agent VIRL to take advantage of the superior exploration behavior of VIRL while learning. So in the cited paper here, each microagent has a shared Q and V function and its own independent policy. So each agent reads from a global replay buffer, and during training, they optimize the Q and V are shared, and then at test time, the policy only uses local information. So on the test set, the agents can only see their own local state to make decisions. So we evaluated MA VIRL on 3 environments to measure its efficacy. The first is predator-prey, where multiple agents chase a prey with landmarks; physical deception, where agents cooperate to reach a single point of interest; and keep away, where a team of agents must reach a point of interest while avoiding an adversary. So comparing with one, our MA VIRL implementation seems to outperform existing methods, namely MERL and MA-DDPG on the keep away environment. We can see that MERL and MA-DDPG maintain close to random, and our MA VIRL is slightly better random, while the evolutionary algorithms actually have a decrease from random performance. And in the other environments, we further compared MA VIRL with we ran the MA VIRL on physical deception and predator-prey. So for physical deception, the environment in the middle, MA VIRL seems to slowly improve over time, while in predator-prey, it was initially learning well, and then it seemed to collapse back to random. Now, both 1 and 2 cited below did not provide direct learning curve results for physical deception and predator-prey, so we don't know how they actually did on those. We expect that this was quite a difficult environment, which is why the results maybe weren't reported in the paper, but we would have liked to compare directly with them. So the other experiment we did to improve upon the results in the paper is an experiment about the residual error norms. So the residual error norm is defined in the paper as a generic p-norm, but the author's code implements a 2-norm, and there's no ablation comparing the different norms. So we thought that different norms may have effects varying with the dimensionality of environments, and so we performed this study. So we observed that the 1 norm outperformed the 2 norm in ANT v2. However, the 2 norm performed better in the humanoid stand-up environment. So in both cases, the 1 norm seemed to be very stable, while the 2 norm was kind of variable, but our suspicions were confirmed because dependent on the task, 1 norm may outperform the other, but it's clear that the choice is between 1 and 2, because the infinity norm failed to learn on any task. So the key takeaways from our experience with this project is that 1, RL environments are messy. So it's usually hard to know which version was used, and there's multiple libraries that we need for an experiment that are kind of co-evolving together. So one project may use a certain MuJoCo, a certain Gim, a certain RL kit that has the baselines, and it's almost impossible to know exactly which versions were used unless the authors give very explicit version information. So a large portion of our programming time was spent on environment issues. Dependency versions are a pain, as I mentioned, and the results in the papers are also kind of hard to interpret and reproduce, because most results are often only learning curves which need to be visually inspected, and if one wants to compare to those baselines, then all new papers must rerun each experiment because the data used to create the charts is not necessarily available. So training requires resources and time for iterating on experiments. So we come from different areas of deep learning research where we can iterate on our experiments rather quickly because the data sets are all standard and quick and easy to load, and we can find out really quick if our current experiment works or not, which allows us to move much quicker. Whereas if we have to wait a day and a half to see if something worked, then it takes much more time and is less convenient. So all of these things make reinforcement learning difficult in our opinion, but we think they also represent areas where improvements can be made, because if RL were to become easier and more convenient for everyone to experiment with, there would likely be more progress in the field. So we have now completed our final representation, and that is the end of our project. So thank you for listening. Bye.